We move from with cosmology to megaparsec scale, is it right? To galaxy cluster. So yeah, please.
Okay, so thank you very much for sharing my work. I'm now a postdoc at the IAG, and I'm still working with galaxy clusters, but not this kind of. So what I'm presenting today is what I've done during my PhD. So my two presentations, but I hope you enjoy it. So I'm going to show a little bit of the introduction, what I'm talking about, the methods that I use, some results with simulations, and with real data. And each of these parts, I'm going to stop a little bit to show a summary. So if you have any questions, you can ask, or I will just go on. Okay, so our universe is composed of several structures, such as galaxies, groups, and galaxy groups, filaments, and these regions of low density, which we call voids. And the formation of these structures is basically affected by this hierarchical formation theory, where these low mass structures merge, giving rise to these more massive structures. Besides, the galaxy clusters have a privileged position as the largest gravitationally bound structures in the universe, which already achieve some kind of equilibrium in this process. So we can study these structures at different redshifts of our universe and try to understand the underlying cosmology within these clusters. And so just one introduction about galaxy groups and clusters. So we have this difference of the number of galaxies. So a galaxy group will have some kind of dozens of galaxies with low masses, so 10 to 13 solar masses, and also small radius, something around 1 megaparsec. When we are talking about galaxy clusters, we have hundreds or even thousands of galaxies inside of it with higher masses, both 10 to 14 solar masses, and also a little bit larger radius. And an important part of this study is this beginning of the classification schemes for a galaxy cluster. So everything started with Abel. And in 1958, he was able to catalog 2,700 clusters, and he done everything by eye. And this classification, he said that a cluster will have more than 50 galaxies within this magnitude range of the third brightest galaxy and M3 plus 2, and with a radius around 1.5 megaparsecs. But now,
Which distance you look at those?
It's close, I think, below 0.02. 0.2, sorry. And now we have these new observations and surveys that will have given us a lot of data, and we need computational power and also better techniques than looking each one by eye. And this is done with what we call as cluster finders, which uses different computational methodologies and definitions to characterize what is a cluster. There are several of them in the literature. Some of them is based on the projected coordinates of the galaxies and also the photometric redshift. And others depends on color filters, luminosity, or density profiles. For example, this wave is cluster finder that depends on this distribution of galaxies, the coordinated projected coordinates. While Amico is one of these filtering algorithms that depends on the colors and the distance from the center of these profiles. But why this is important? So the idea is that galaxy clusters can be used as a tool to constrain cosmological parameters. But to do that, we need a large amount of clusters and also very precise mass estimates for these clusters. And this can be quite difficult to obtain depending on the number of clusters that we are using, because some methods like X-ray analysis or gravitational lensing can be very expensive depending on these numbers, and they're usually a lot. So what we do is use this mass observable relation, where we can relate the mass to this observable, which is easier to obtain from the observations. just like richness or the optical luminosity or even the X-ray luminosity or the SNIF average effect, things like that. And in my work, I was trying to develop these mass proxy to use in the clusters. So the idea then what would be a good mass proxy? It must have a small intrinsic scatter. So we have this precise mass measurements for the clusters. Have a small dependence on the cluster dynamic state, as we are considering different clusters around the history of the universe. Some of them might be passing through some merger event, so some easy and some approach can be affected by that, and we don't want that to happen. And also be easily accessed to the observations, so we can do the analysis without any problems. And there's some of them, the literature, which already has a small intrinsic scatter between 0.2 to 0.3 flats. Goals like the X-ray luminosities, and observation effects, stellar mass, and optical richness. But we wanted to go even further, achieving these small values of intrinsic scatter using the photometric information, the photometric surveys, not the spectroscopy. But as every method has its problems, when we're talking about the photometric information, we need to deal with these photometric errors. A typical error of around 0.01 corresponds to 3,000 kilometers per second, which is 3 to 6 times the velocity dispersion of a cluster. So what this means that we will have contamination by this galaxy that is along the line of sight, that will probably lead a cluster which is not actually bounded by gravity, but because of this effect of cosmic projection. And at least for the membership analysis, we have already in the literature some way to deal with this contamination, which is by using probability membership. So here I'm just showing some of these works that come from 2016 until now. And so by membership, what I mean is that instead of saying that a galaxy is a member or not of a cluster, we give a membership probability. So we can apply cuts to try to remove this contamination by this projection effect. So here I'm talking about these imaging surveys of the photometric branches, which use a combination of broadband filters and also the narrowband filters. Here I have the two of them that I'm using this work, which is S plus HFS. And one interesting part of this is that with this information, we can use also the probability density functions of the PDFs. So instead of having only one value, we have this distribution, which will allow us to have a better description of the data. And this is very interesting for the cluster analysis because the methodologies that we're using to detect these clusters are migrated from a color-based approach, just like RedMapper. I don't know if you read it. But RedMapper uses the red sequence of the cluster to detect a cluster. But now we have more information than just colors. So we can use galaxy over density, which is the case of PZ-Wave. And PZ-Wave is the methodology that I'm using for my work. So here we have as data, and you can see the projection of all the galaxies. And what PZ-Wave does is separate this data into different redshift sizes. So going from 0.05 until 0.8. So we have different redshift beams. For each of these redshift beams, PZ-Wave will weight the galaxy using the PDF, and will give this value depending on this integrated value of the photometric redshift. So depending on these limits of the redshift. So what happens then is that it's going to create these density maps to try to find the galaxy clusters. It will also apply a difference of Gaussian kernel, which will smooth these structures that are below or above the sigma that we are using. And we put at the minimal value of 0.4 megaparsecs to detect the structures, and the largest one will be 1.4 megaparsecs. And after that, we have the calculation of the signal to noise. This way we will just scramble everything in this area and then calculate at each point a signal to noise. We are taking everything above the signal to noise support. Okay, so, but the problem is that when we are doing this step of going from the galaxies to the density maps, we lose the information about the galaxy. We just don't know anymore what kind of galaxy belongs to that cluster or not. So I developed this membership estimator that we call as UMIC, and that we will use the same methodology of PZ-wave of calculating these probabilities using the PDFs. So here I'm going to show a little bit of details of how it works. So in that cluster, we can use to any catalog actually, which has the central coordinates of the cluster, the redshift, and also the same information for the galaxies and also the PDFs. So it's quite agnostic. We're just needing this information. So first we select all the galaxies within fixed radius and redshift, creating like a cylinder. Here we are just throwing away everything that we know that will not be connected to the cluster center to reduce the computational power of that. And then we detect a break in the galaxy density profile. So here you can see that goes from the cluster center to the outskirts. And eventually we will have this drop in the profile. And this is what we are calling as strategic radius of the cluster. We will calculate the memberships inside this radius. So for each of these galaxies, we draw a random redshift, which is based on the PDF. And then we calculate the cluster velocity dispersion to try to remove these galaxies that, because of this random draw of the PDF, can end up higher than the cluster redshift. So we just remove them, which is ones that I go too far away from the cluster redshift. And then we run HTTP scan, which is the integrated algorithm that will connect the points in this projected space and say, oh, this seems connected, but this one that's too far away is not. So this will be an outlier. And then we repeat the steps several times, like 100 times. We can use all the PDF information and have this membership probability, which will be the number of times that a galaxy is selected as a member over the number of times that we run this process. And here, so HTTP scan, it is a code developed by Paulo et al. In 2013. And what it does is to calculate the distance between the points in the projected space, create some kind of distance parameter here, and then we will connect the clusters, the galaxies inside these small regions. And then the ones that are too far away are the interlopers. Okay, so let's imagine how this works in a more simplified way. So here the blue points are the galaxies, and the X is my cluster center. I just throw away everything that I know is not connected to this cluster, like above 2.5 megaparsecs and within 3 sigma, which is the error of the photometric redshift. And then we estimate the galaxy density profile. We have our characteristic radius. We throw everything away again. And then with that, oh, I forgot to say, but we consider that when we have this drop, it's because the cluster stopped being dominated by its member galaxies and start being dominated by these few galaxies. So you're throwing away these few galaxies.
So the red circle there is the gray line in this sub.
Exactly. And then we draw the random redshifts from these PDFs. We do the 3 sigma clipping. And this is an interesting step because we will know how important is this galaxy for the cluster distribution. And then we will do it 100 times. And then we have the membership probability. And here I have 2 real cases of clusters detected on using S-Log data. So in the high region and the strike-82 region. Here, the colors, the direct colors, and also the size of the points means that we have more probability of this galaxy being a member of the cluster. You can see here that even this red galaxy here. Even being close to the center probably has a different redshift, so the probability of being a member will be reduced. Okay, so now we have this method. We can apply the simulations where we know exactly which galaxies belong or not to the cluster and see how well our code is behaving. And we have published a paper about that. So here we are using this simulated catalog from IAG 2021, which was created to reproduce the first data release of S+, which is just these striped two areas. And here I have a sample of 919 galaxy clusters and groups. You can see the redshift distribution here from 0.05 to 0.45, which is the same range of S+. And also these ranges of masses that goes between 12.8 until 15.5. And this quite Gaussian form can be a little bit strange, but this is because we needed to apply a fillet in the membership of these mock galaxies, mock clusters. Because of the way this is created, we need a halo population model, which will distribute galaxies for each halo, and we will have some spread of these halos too. So we remove everything that has a membership of galaxies lower than 3. So we at least need 3 galaxies to say that that's a cluster. So the final distribution ends up like that. And we calculate the richness inside characteristic radius for these small clusters, which is the sum of the galaxy's membership probability. If it's a mock, so if it's a member, it's 1. If it's not, it's 0. So it's just this sum. But in the real data, we will have something like a richness of 4.5 or 4.9, anything like that. It's not that perfect. And also we try the optical luminosity, which is calculated like that, depending on the absolute magnitude in R band, and also the total stellar mass of the cluster, which is also everything weighted by this membership probability. Okay, so how well we're recovering these true values from the simulations. So here I'm showing to you these richness that are calculated inside the characteristic radius with the ones that I calculated with using my method. And as I mentioned before, you can see that for the true richness, we don't have errors in the x-axis. And that's because we have like 4 or 5 or 6 as richness. And when I'm calculating my richness, it can be different. So, and this last point, there are errors, but because I'm forcing them to have at least 10 clusters inside each beam. That's like this. We have this error. But you can see that the median points show a very nice relation to one-to-one line. So great. And when we do this calculation of the true richness with the richness calculated with my method, one by one, we see a small deviation from 0, but it's very small. So we were very happy with our results.
Why aren't there clusters with 7 or 9 richness? This
Yeah.
it's funny.
Yeah.
These are like you said, these are just integers, right? So,
Okay, so our idea was to do everything to create these scaling relations where we could use this mass proxy to relate with the mass. So here you can see what we are obtaining using this richness value with the masses given by the simulations. Here the data points are the values obtained with simulations, and the red ones with my code. And these linear regressions were done by NumMix, which is a code which does this kind of thing. And it returns a parameter, intrinsic parameter, this eta, which will give us the intrinsic header of the relation. So lower this value, better is our relation, and better will be our massive result. This first results that I'm showing for you. So the first line is the one obtained with the simulations, and the second one is the one with our method. So you can see that the values are quite close. We go from 0.18 to 0.14 in using the optical mass of the cluster. And this is the results for the total stellar mass, 0.092 or 0.97, which is great. Just come back a little bit. You can see that the last point is a little bit away from the one from simulation. And that's because when we are considering these clusters with high masses, we end up with more contamination of these few galaxies. When we have a group of galaxies, they are usually more concentrated, so it's easier to separate them from the few galaxies. But the galaxy cluster is a little bit harder. So that's why we have to get there. And again, the total stellar mass. So this was a great result, but we need to remember that these are simulations. They're simulations. And these stellar masses are calculated using these analytical functions. And when we do that with real data, we end up introducing more errors in these estimations. But this is a great result. But again, how this would affect when we calculate this richness using detection code. It will not be the same that one given by the simulation. So how these small offsets in the center and in the redshift will affect our richness results. So in our study of 2022, Stephanie worked with PC-Wave and applied it in the same model that I'm using here. And she found a difference in the centers of this simulated catalog with the PC-Wave results of only 10 kiloparsecs in difference, with a small deviation there of 12. And you can see for the redshift difference is very, very small. So our idea was to create a function that was centralized in this mean value, and then adding 1, 2, or 3 sigma to spread this data and see what happens. And what we found is that the richness results are not affected by small deviations in the center. They start feeling something when we get this center wrong by 250 kiloparsecs. So yeah, we're just getting very, very bad results for the center. And then we just lose like 5% of this richness. But this is a little bit different when we go far away in the projection space, in the redshift space. So when we go for 2 or 3 sigma, which correspond probably to the photometric effort, we start losing the PDF information. Why? That's why we have these graded values of loss of the richness when we go far away in the redshift. But that's fine because we have very small redshift errors, so don't worry about it. And then part that is nice here is that small offsets are okay for both the rules for this kind of expected differences. And well, I'm talking about the PPS. So in this simulation, we just gone to the easiest way of calculating this PDF, which is a Gaussian, which will have this centralized position in the galaxy redshift, and then 1 or 2 or 3 sigmas, depending on the photometric error, depending on the magnitude of galaxy. But still, they are Gaussians. What happens if they are not Gaussians? Because in the real data, we have these strange behaviors of multiple peaks or larger rings. So how will that change our results? So for the larger rings, we use a T-student distribution. And we found that even if all the galaxies are affected by this behavior, we only use like 2% of this richness, which is okay. But binary becomes more problematic if it's affecting more than like 12% of the sample. And by saying by modality, I'm saying that the second peak must have at least 20% of the first peak in this height. And also a difference in the redshift, like the 0.05, which is again 3 sigma all the photometric error. But when I try to estimate that these kind of contaminations for both S plus and mid-JPS data, found that they are lower than 10%. So our test, it shouldn't be major error related to our business results. And this is the summary of Act 1. You want to make any questions about that?
So sometimes you have bimodality just because you have two systems which are close by. That what happens, or
It's actually for the galaxy. So the galaxy is not well resolved. So sometimes it can have a peak in the
in the
filter
PDF
system.
of the
Yes.
photo Z. Oh, you're talking about the photo Z,
The photo
yes,
Z,
not the
yes.
cluster. Right. And
So I'm going. So my first results with mini JPS. So we applied, we also published a paper about that the end of last year. And so JPS is this photometric survey which use several narrowband filters. And you see here 55 filters, 54, sorry. 3 of them is broadband filters and 51 is the narrowband filters. And we have photometric error around 0.013. And here the results are with mini JPS, which is a small area of only 1 square degree, which was launched as a pathfinder to test our methods and see how well we could perform our detections and analysis. And here, applying this wave, I found 574 groups and cluster candidates in this small area within the redshift range of 0.05 to 0.8. When we compare with the other cluster finders running in the same area, we got a little bit scared because the ones will find like 150 clusters. So what the hell is happening here? And we figured out it later that that's probably because the way this wave calculated signal channels, as this is a small area, has a problem in calculating this and just accepted everything that has a small peak. So we're being selected a lot of junk with that. But we have the richness results for all of these detections. So we saw when applying a richness cut, so try to remove some of these contaminations. And for that, we followed this plain et al. Procedure, which is based on the richness. So what we do is to draw random points within these coordinates and calculate the richness for these random points. And then for each of the clusters detected by this wave, we see how many of these random points have a richness result lower than the Pisa wave richness. So yes, for different redshift bits, depending on the cluster redshift. And we can then apply a significance threshold for these detections. So when we put this threshold in 90%, we are removing everything that would be a detection by chance. As they have like this random distribution, it's just like a detection by chance. Just throwing everything away. And then this was a better result. We go to 221 clusters detected on this area.
sorry, what is M?
Yes, it's the magnitude, the absolute magnitude. That I'm going to explain now. So the idea here is that we need to avoid the incompleteness of the catalog, the Galaxy catalog. So that we apply different magnitude cuts, in absolute magnitude cuts, to try to remove these faint galaxies that we are not actually observing at high pressures. So we saw that when we apply this first cut that goes into 0.8, we start losing lots of galaxies in this low redshift range. So we decided to apply 2 different cuts, one for the low redshift and one for the high redshift. And then just cut the catalog in different, depending on the redshift that the galaxy, the cluster needs. And here we just call that group regime and cluster regime, but this doesn't mean that if the group of the cluster is detected at low redshift, it is a group or a cluster. It's just like a way we just trying to say that we're giving more importance for the group regime in this low redshift range. And then we have like this better way of constraining the radiations for these low structures without losing all the galaxies. And with this catalog, we compare to AGET and AGE's X-ray field, which is an overlapping area with mini JPEGs. And this catalog of F1 were already published and were established in the literature. And this is the dark circles, and the stars are the one that I found easy wave. And what we done was to reanalyze both Chandra and XMM data, X-ray data, try to find new matches between our catalog and these X-ray emissions. And the one who do that was Alexis Vinovenov, who also worked with F1, so he already know everything that he needed to do. So we just have these nice results. Yes, because the overlapping is not perfect. Some part of this BJPS area just the area. And that's why we have this very massive structure detected there and don't have Aegis X-ray detected there. No. And this guy was taken as object of study of collaboration. So we have a paper only talking about this guy. It was known as the mini big guy. And also highlighting here this group that we recovered at this high redshift of 0.75 with only 4, 10 to 13 solar masses. So it was super interesting that we could find the structures as so high redshift. At least for us, it's very high redshift. And this shows the quality of the data that we have and also the methods that we are using. And here the masses were calculated by a little development paper using the weak lensing calibration. So we have this calibration with lensing.
Sorry, can you go back?
Yes.
So what about the X-ray systems that are not being found with PZ-Wave or, I mean, yeah, the ones that are not found, did you manage to find them with your algorithm or they are missing for some of the same reasons? They are not really overlapping as well.
Yeah, some of them are because of that, and some of them are in this overlapping position, but I don't know exactly why we couldn't find them. It wasn't clear why. Okay, so as I mentioned, we had other classified algorithms being applied to the mini JPEGs. So we compare how well they behave in this area comparing the three of them. And we call as a matching when we have a center distance below 0.5 megaparsecs, and this difference is redshift of 0.05, which is again 3 times the photometric error. And here we have Amico, which is a filtering clustering algorithm, and also BT, which comes from Voronoi tessellation, which is a pure geometrical code. And the interesting part here is the center distance of these matching clusters, 43 common clusters between them, is that the center difference is around 100 kiloparsecs with a deviation of only 60. And when we go to the difference between the redshift, it goes 0.001. So it's very small error for these redshift estimates. So we are very happy with that. And as a final study of these catalogs, we try to analyze the significance of these detections. So we expect that at least one massive galaxy will be centralized in these clusters, will be found in these clusters. So we use this catalog of massive galaxies. And using these relations of those ideas at all, 2018, we compared the halo mass with the central galaxy stellar mass. And the first thing was trying to find how many of these massive galaxies were isolated in the mini GPAS area. And here we have two different redshift ranges. The simple ones are then for the small range of the redshift. And we have a nice recovery of these massive stars, massive galaxies, sorry. And when we go to higher redshift ranges, we start losing like 60% of them, which is quite bad. But this wave is able to recover more of them because this catalog is also larger. So we have a better way of constraining a little bit these structures, but we are also more contaminated. So it's this trade-off, which is kind of hard to balance. And here I have this mass distribution in the redshift ranges using the Scott-Elias et al. Relation between the BCG stellar mass and the halo mass. And we find masses that goes from 5, 10 to 30 solar masses until 1 to 10 to 14, which is similar to the range that we found in the X-rays. So it was great. And this is the summary of part 2. And I'm just going for the part 3, which is my results using the S-plus data. So if you are using the R4, now we already have the IDR5, which is a little bit larger. It has already 4,050 square degrees observed. And S-plus aims to observe at least 9,000 square degrees. So kind of the half of the way. And here we're using 12 bands. 5 of them are the broadband ones and 7 is the narrowband ones. And here the photometric errors are around 0.02. And here is the area that I have found clusters. So 72, S+S, MC, S+M, and Hydra. We are removing S+D because of its focus on the Milky Way disk. And so this is 3,000 square degrees for the ER4. We're going to magnitude of 21. And I put there redshift of 0.05, but actually we go until 0.4. And here just some numbers of the galaxies that we found within each area and also the number of clusters that we detected. And I just wanted to highlight our first results with the first AWPs. So we found only 450,000 galaxy clusters within this stability area. And have a lot more. And you may be wondering if they are reliable or not. So when I tried to analyze using simulation, I found that if we put a richness threshold of 2.9, we end up with a catalog which is 95% complete and 80% pure. And here is a comparison between other catalogs found in stability area. Both from X-rays, when it was a garbage, and also other optical catalogs. And it would be quite hard to compare directly the optical catalogs because it depends on the magnitude of the galaxies that they are considering and also the algorithm that it's considering for detecting these clusters. So it's not that easy.
So is this completeness?
Yes, it's complete.
That's comparing 80% that you have.
And we can see that we are behaving better this redshift range of 0.1 to 0.4. But before talking about that, I would like to highlight our own results. We have only a 50% match with the old catalog, and it was kind of a surprise. And here, when I took to look at the data, I found like the black ones are the matches. The blue ones are the results from the year 1, and the red ones are my catalog with year 2. And you can see that we have some kind of border effects, which increase the number of detection in this area, which I was able to remove them later. But with year 1, we didn't know that yet. And we also have slide here, I don't know if you can see, but this is a straight line there, which is caused by this overlapping of the detections of the images. So we have this false over densities over there. We wasn't aware of that before. Then this wave as density-based algorithm, at the time that he found these over densities, yeah, this is a cluster, but it wasn't. So that's why we have this 5G progress.
Are these repeated objects, or these are just the fact that you have greater depth in a certain slice there?
Yeah, we can have both. We have a little bit of problem.
Both a bug and a feature.
Yes. But this is better here for it. And just as I mentioned, the different fractions between 0.4 and 0.5. So we have this incompleteness of the catalog for the higher redshift ranges, which is okay, but we at least know about it. And then you can see that the match fraction is better for these redshift rankings, lower than 0.4. And here, just a comparison between centers and redshift offsets. And the center depends also on the way you are considering the center by the algorithm that you are using. So is that the BCG or the X-ray peak, or I don't know, the overdensity like piezo wave. So it's quite hard to compare them. That's okay. It's lower than the 250 kiloparsecs that we found that should be best for our richness membership estimator. And very small differences for the redshift values too. So 0.002, which is great. And that's the summary for part 3. And that's all. Thank you for your attention.
Do you plan to, you have simulations that you can use to know the selection effects on your, and the purity, the completeness, and so on. Do you plan to have something like mass function, halo mass function, and then some cosmology from this data set, or is this a little bit more in the future?
It was the plan of my thesis, but I didn't have time to go there, unfortunately. So for now, it just stop it like that. I'm not going to go further than that.
You have a postdoc to go there.
But it would be very interesting if you could do something with this sample, because it's a very nice sample.
Yeah, basically, I'm curious to know what can you envisage you can do with this information with cosmology. So what you learn about
Yeah, you didn't have time to work on that. Yeah, well, not me, but someone related to our group. That's not my changing my focus.
So who is so the same work is continuing in JPass now, and we have the public data release at the end of the year. Who is being the new Lia in the cluster group in JPass?
Still me.
Your view is to you.
Yes.
Okay. So you haven't shifted entirely.
Yeah, not entirely. But
Okay.
now I'm just producing the catalogs, I'm not analyzing them.
Okay.
Okay, so food is ready downstairs, so we have one talk in the afternoon. And before we take, remind you, we have the next meeting on the October the 11th, so we don't have speakers yet. So can volunteer yourself or volunteer somebody. And so on the 11th, we have to find 3 speakers, but we do it later. So the meeting for today is ended, but of course, after lunch, you can use the premises of the institute and sit in the offices and discuss and do wonderful science. Thank you. Yeah.
Thank you.
You.